water shortage. It's one of the most severe problems we face today. It affects so many people around the world. One of the places we're all familiar with is Africa. But it might interest you to know that in fact Africa has enough rainfall to supply its entire population 1.5 times over. The problem is therefore not a lack of supply, but rather a failure to effectively or efficiently utilize this water. Rainwater harvesting is a method that has been proposed whereby roof water is collected and stored, and when it is required by a household, it is pumped and filtered for use. However, the power supply for the pump and filter is unreliable in these areas. Such remote and rural villages suffer from blackouts regularly. That is why we have designed and implemented a renewable energy system for powering rural households. It is reliable, cost-effective, and efficient. Such a system consists of a renewable energy source. We have chosen solar power because in developing countries it tends to be more cost-effective in the long term compared to other alternatives. The system also comprises of a local load. This represents any household appliance, say a washing machine, a water pump, or even lights. The power from the solar panel has to be conditioned before it can be supplied to the local load. A boost converter is used to step up the low solar panel voltage so that an inverter can convert this to an AC voltage suitable for appliances. To increase the reliability of our system, which is essential in a remote or rural village with an unreliable grid supply, we have added a battery bank to our system. This battery bank is interfaced through a bidirectional boost converter. By connecting our system to the grid, we are able to supply power back to the grid as well as consume power. Feed-in tariff programs, which are gaining popularity in developing countries, allows money to be earned back in exchange for power supply to the grid. This increases the cost effectiveness of our system. Clearly, the inverter has to operate in two modes. The first is standalone mode, when it is connected to only the local load, and the other is grid-tied mode, where it is connected to both the grid and the local load. In both these modes, power flow through the boost converter as well as the inverter has to be controlled while maintaining a high efficiency. In addition, the inverter can be controlled to allow bidirectional power flow. It is clear that a sophisticated controller is required. That is why we have chosen a Texas Instruments digital signal processor for this purpose.
To achieve what we have set out to do in the limited amount of time that we were given, we have decided to use Simulink Inverter Coder. This is a feature found in newer versions of MATLAB and Simulink. And what it does is that it allows us to take Simulink blocks and compile them into C code, which can then be compiled into machine code for the DSP. This means that we can actually save a whole lot of development time by going straight from simulating this control system in Simulink and go directly to implementing it with no intermediate step. Another advantage of using Simulink Inverter Coder is that we can visualize the entire system in Simulink blocks, making it a whole lot easier for us to debug when things indeed go wrong. Let's take a closer look at the control system that we have developed in Simulink.
During the development of our converter, we have simulated our single-phase inverter with power electronic components from the Plex toolbox on Simulink. And after we were satisfied with the results, all we had to do was copy and paste the control blocks into our DSP project. Here's a shot of the code that was compiled into the DSP. As you can see, the embedded coder allows me to set up the chip through drop-down menus and dialog boxes. In current mode control, the grid voltage is sensed and passed through a phase-out loop. Using PI compensation, this produces an in-phase current reference. The proportional resonant controller is mathematically a frequency-shifted PI controller that achieves zero steady-state error when it is checking a sinusoidal signal of the resonant frequency, and in this case, it is the grid voltage. The correct output is then sent to the PWM channels to be output to the inverter. Switching between voltage mode control and current mode control is currently done through the SCI, and an embedded MATLAB script was written to interface the SCI and output significant parameters when requested. The resultant system performed well. In a 20 ohm step load change, the controller was able to regulate the voltage with a transient disturbance of about 1 millisecond, which is really good for a grid-tied inverter. One thing to note is that this is our first Simulink project, and the learning process could even be said to be pleasant. The embedded coder is well documented, and from what I have shown you, it allowed us to simplify a time-consuming embedded coding project into one simple Simulink model.
Using Simulink, we have developed a system that's going to help people in the third world countries. What have you been doing with your time?